Hello, I'm Anna Mackay and we're looking at vector projection. So imagining the vector A, which has components 2, 3, so 2 in the horizontal direction and 3 in the vertical direction. The projection of this onto the y-axis to start with. So it's the shadow essentially that it casts onto the y-axis. Imagining the sun here and all of the rays that it would be creating, and therefore where the shadow would be, where it blocks out the light, on the y-axis would be here. Having a think about how long that would be. What part of that length relates to vector A? It's the vertical component there. And the vertical component has length 3, if you like, which is 3 lots of j. So where j is what? Do you remember? It's a unit vector with length 1 in the vertical direction. And so it's 3 lots of that unit vector. What about the projection on the x-axis horizontally? So what shadow does vector A cast on that x-axis there? Imagining the sun's rays and where the light is blocked out by vector A, we'd be left with this projection vector of vector A on the x-axis. And how long would that be? It's the horizontal component of vector A, which is 2, or the unit vector 2i. Now what about the projection of vector A onto vector B? Imagining light, again, being cast onto A, and where is the light not hitting B? So what's the shadow of A on vector B? That's the projection vector that we'd have, and thinking about how long that would be. And noticing the direction we had here, the first one went the direction of A, and therefore the direction of the projection vector. And if A was in the opposite direction, the direction of the projection vector is in that opposite direction, so more in the direction of A. What about the projection vector of vector B on A? So the shadow that it would cast on A. Now we know A itself is not the same length as B, but you can still imagine approximately what that would be like. That it's the length along A is the projection vector there. Noticing the right angles that they meet at here, if you were to extend from the tip and the tail. Now how do we work this out? So the projection vector, we're just going to unpack this a little bit. So we've got the length of A, cos theta, and B, that's the unit vector. I'll explain a few parts to this. If we're after the length here, we'll call PQ, so this side here, using right-angled trigonometry, how could we work out PQ? Well, in relation to that phi angle, that is the adjacent side, and therefore vector A is the hypotenuse. So we would use cos. Cos of an angle is the adjacent over the hypotenuse. The adjacent is PQ, and the hypotenuse is vector A. Rearranging that for PQ, we get vector A multiplied by cos of phi, I should have said. Now you can see the similarities here with the formula that I've given you. We want the length of that line though. So we need the magnitude of vector A, which you can see is there, and we're saying that cos of phi is equal to essentially the length of that angle, so the modulus, and then that will be a scalar multiple. So if you look down here, we've got the length of A and cos of theta, so it's the cos of that angle. That'll be the scalar component, how long it is, versus, multiplied by the unit vector of B. So we're interested in the unit vector in the direction of B, and how many of those unit vectors do we want? We want it to be the length of PQ, and the PQ is this here, the magnitude of A multiplied by cos of that angle. Right, just unpacking that formula a little bit more here. The unit vector of B, if you look back on previous work on unit vectors, is vector B with 1 over the length of B. Rearranging a bit more here, notice I've put the magnitude of B on as the denominator. Next line here, we've multiplied top and bottom by the magnitude of B, which essentially is multiplying by 1, so it's doing nothing. We are trying to work out the angle here without knowing the angle. Do you recognize this? This comes from the previous work we did on the angle between two vectors, and that is equal to the dot product of A and B, or the scalar product. So as you can see here, that's been substituted in for this. And just rewriting that again, just putting that there. Notice you could split this because it's squared, so there's two lots of the magnitude of B on the bottom, and therefore the scalar part of that is the length, where that is the magnitude of the dot product over the magnitude of B. And that's the length, the scalar multiple parts. That's how many lots of the unit vector of B that we're going to have. I know that's a lot to take in. As you do some examples, you'll be able to put this into practice. So here's one here. We're asked to find the projection vector of A on B and state its length. Feel free to draw yourself a little picture of what those vectors might look like in relation to each other. The thing is, you don't know where they are. You might try and draw them and thinking about the right angles that would happen. I'm not going to go into too much, not going to go into that at all today. All right, so vector A, I like to write it horizontally, and vector B is that. So looking at the formula that we're going to need, at some point we need to work out the dot product, the scalar product. That's where you multiply corresponding components. So we've got 2 from vector A there, multiplied by -3, and we're going to add on 3 multiplied by 5. That gives us -6 plus 15, which is equal to 9. So that's the dot product. What else in this formula do we need? We need the magnitude of B. Let's work that out. So we look at the components of B, we square them, -3 squared, add 5 squared, and the square root of all that gives us 9 plus 25, which is the square root of 34. Putting that together, we're asked to find the projection vector. I'm just going to write that out. I'm going to write out the formula because I find that really helpful to get my head around which components that I need to use. So the dot product was 9, and the magnitude of B was square root of 34, and it's saying we square that, so we're left with 34 there, and then that's multiplied by vector B. So reading the question, find the projection vector. So check, we've done that, and state its length. 2 ways of thinking about this. You can follow the length formula that we've got over here and just substitute the numbers in, which would give you the size of the dot product, well, the modulus was 9, and that's over what we've got here is the magnitude of B, which was the square root of 34. So that's using the formula. Or the other way to think of it is looking at the answer that you got, this projection vector. If you're asked to work out the length of that, you need to use the formula where we work out the length of a vector. I'll just put this, I guess, scalar out the front, and the length of a vector is where you square each term and take the square root of all that, and that would be equal to the scalar out the front, and it's the square root of 34, and your third laws would tell you how you could rewrite that, and that's 9 over root 34. So you're still going to get the same answer. You can either use the formula for length, or if you get stuck, just go back to thinking, how do I work out the length of a vector normally? You do the formula on that part, and then you incorporate the scalar at the end. If you like this video, give it a thumbs up and subscribe to the channel. And the next one in this series is proof using vector geometry. Thank you.